Yeah, welcome after this, after the cool keynotes in this morning and the nice break to the next session. It's called Avatars 2. My name is Florian Weidner, and I'm going to chair you through this session. And the first talk we start right away is Audience Amplified, Virtual Audiences in Asynchronously Performed AR Theater. The presenter is You-Jin Kim, and he's a forthcoming assistant professor at Texas A&M University, and he's presently completing his PhD at UC Santa Barbara. His research interests include mobile agents, mixed reality, and immersive theater. And you press the microphone. Thank you.
Hi, everybody. It is my honor to present our work, Audience Amplified, Virtual Audience in Asynchronously Performed AR Theater. I'm You-Jin Kim from UC Santa Barbara, and in the process of transitioning to assistant professor at Texas A&M. And I had the honor to work with Misha and Tobias Höllerer on this project. Our project, Audience Amplify, is a proof-of-concept augmented reality theater system that allows users to walk and see performance in each area of the AR stage. We demonstrate how AI-trained virtual audiences can create a social experiment, allowing users to experience the atmosphere of live event at any time. Recent research has demonstrated how virtual audience or NPC can influence or enhance user experience and invoke sentiment of a live concert. Some VR projects specifically explore the role of virtual audience in inducing concert-like experience. These studies have paved the way for our experiment, which involved AI virtual audiences trained for and in specific physical layout. In our study, we used the standalone AR headset, HoloLens 2, to enable a solitary user walking around and enjoying performance on 208 square meter AR stage. Our AR play features 3 content zones where dancers appear, perform, and disappear once their performance is complete. If the user feels lost, they can look down to see the arrow guides them to the next content zone, as you can see here. So for trial with the audience, these virtual audience spawn next to ticket booths and join the experience. Our virtual audience is trained to simulate human behavior within the physical layout as the AR theater unfolds. In the second pilot study and the main study, dancer was placed in each content zone, and 3 female and 3 male virtual audience members were present for the trial with audiences. We carefully considered the height of these avatars to study how it impacts the user experience, as research suggests that height manipulation affects experience in virtual reality. Our project aimed to explore the following objectives. Can the addition of virtual audience enhance the user experience in AR theater by creating a more social, personalized environment similar to live event? What is an appropriate training methodology for believable audience agent? We believe training ML agent using imitation learning could be our solution. How do such a trained agent compare to state-of-the-art NPC model? Can AI agent learn location-specific behaviors? We investigated these questions and present our finding here. To investigate our questions, we conducted a series of user studies, as you can see here. Pilot study 1 had 20 participants. The main goal of the pilot study 1 was to evaluate and select the best avatar for our animation. Pilot study 2 enlisted 10 participants and explore which of 3 different implementations of virtual audience would be most effective for our study. Here we compared audience among 3 audience types: audience sound only, NPC audience, and deep neural network audience. The main study features 20 participants and investigated the impact of virtual audience of user experience during a dance performance in AR theater. We ensure that Participants are not shared among Pilot Study 1, Pilot Study 2, and the main study, and we recruited 50 users for this study. Pilot Study 1 evaluated the best avatar among the icon avatar, 4 idle state avatar, and 16 idle state avatar you see here. Participants favored the 4 idle state avatar for the unobstructed and natural behavior it presented. In contrast, the 16 state avatar was seen too distracting and expressive movement for the users to enjoy. As a result, we decided to proceed with the 4 idle state avatar for our subsequent study. We employed several techniques to enhance the animation of our avatar. An animation control was used to smooth out the transition between idle state. Motion matching technology was used to allow seamless transition between different motion based on the path and the speed of the avatar movement. And action buffer were used in training management to continuously input the controlling the avatar. And this function of the approach actually helps prevent overlapping action, resulting more natural movement. So we use these 3 collectively to smooth out our animation. Okay. We developed 6 deep neural network models, 1 for each virtual audiences member, using data collected from previous users during earlier trials. These models were trained using data from 60 trials, totaling 3 hours, 21 minutes, tracking data from users watching the AR play. This data included information on user interaction within the environment and the content zone. To expedite our training session, we conducted a concurrent session of 18 virtual environments, learning from user movement playbacks. Here we zoom into one of the training environments, highlighting how AI can learn both physical layout and tracking of user activity using imitation learning. The reward system was refined to encourage behavior aligned with watching performance and walking. Detailed parameters are presented in our paper. So while there were several differences between NPC and DNN virtual audiences, one notable observation that NPC appeared was to they had a much intentional in their movement. So conversely, the DNN audience exhibited more wandering behavior, making them appear more independent and distinctively spreading out during the performance viewing. In pilot study 2, we evaluated the effectiveness of 3 virtual audience types: sound of audience only, NPC audience, and DNN audiences. Results show that presence of virtual audience was preferred, and DNN turned out to be the people's favorite because the experience resembled live event. And there's much more to it, but you can check out the paper for more information there. And so finally, the main study, we proceed with our main study using only the highlighted trial, as you see here, comparing the basic AR dance performance with the most sophisticated AR model. Please note that any result mentioned hereafter refers specifically to this DNN audience model. So to evaluate our user experience, we conducted post-trial inquiry, consists of 38 self-reported questions. We used the guest questionnaire, immersive virtual environment questionnaire, ARI questionnaire, and GEQ to measure 32 components. And here I'm sharing footage. And so these are the deep neural network virtual audiences we deployed. Okay, moving on to the result. Our study showed that participants who experienced the performance with an audience spent more time in the experience and reported higher level of interest, involvement, and investment. Arrow bar here represent 95% confident intervals. Moving on to the height, our results show that a shorter participant reported higher level of immersion, presence, and engagement, along with the greater focus, attention, and desire to interact. This is intriguing as it suggests that height can influence user experience in AR setting. Understanding this further could inform the design of the customization of immersive experience for diverse audiences. So we collected substantial amount of qualitative data from exit interview, which provide valuable insight into our study. One participant mentioned, "I like the trial with other audience because I could walk behind them feeling like I was watching with the crowd of people and not by myself." And these results indicate that people enjoy the presence of virtual audiences, even if for different reasons. So while we received overwhelmingly positive feedback from participants, we acknowledge that this study lacks a direct comparison between real human audiences to our AI audiences, as well as the non-interactive nature of these virtual audiences. So to summarize, overall, Audience Amplify demonstrated that using imitation learning and utilizing digital twin AI agent can replicate human interaction behavior for specific physical space. Also, players' height can impact their level of immersion, presence, and enjoyment level. Based on our result, we believe these AI agents, specifically trained for certain physical layout, are highly versatile and adaptable and can play a supportive role in the future immersive plays. Thank you so much for listening to my talk.
Thank you so much for this talk. Are there any questions from the audience? Yes, I'll just come around, no worries.
Hi, thank you for a great talk. I'm Allie Lyle from UCF. I enjoyed the slide that you showed with some of the qualitative feedback that you got from your participants, and I was wondering what sort of qualitative inquiry you did with them, and if you considered doing some iterative thematic analysis to identify any themes across participants about their experience.
These interviews are mainly used for the next iterative of our study, and because I myself actually is more of a behavior, but also theater immersive play designer myself. So I do use them directly to design my next stage, and some of the insight that we gather shows that like user specifically didn't want to utilize the arrow to navigate to the next stage. And at one moment, they just like start following around the audience. And these audiences are quite nice to follow along than NPC model because their intention is much more human-like behavior. So they stutter, they look back and look around, and all that kind of adds up to the experience, if that makes sense. But I can definitely share more.
Thank you so much, and another round of applause for our speaker.
Thanks.
Great, and next up is Salam Dahir. She is an assistant professor in informatics at the New Jersey Institute of Technology, and her research focuses on using computer graphics, VR and AR to improve training, and doing this especially in the healthcare simulation domain. And she's talking about system usability and technology acceptance of a geriatric embodied virtual human simulation in augmented reality.
Okay, hello everyone, and thank you for the introduction. And I guess I got the microphone out. Okay, 1 second. All right. So, well, my name is Salam Dahir, and I'm presenting today on behalf of my student, Asif Ahmmed. I'm from the New Jersey Institute of Technology, and this project is collaborative between NJIT and University of Central Florida, and it's funded by the National Science Foundation. And today I want to talk about the system usability and technology acceptance of a geriatric embodied virtual human simulation in augmented reality. So the motivation of this work is there are two problems. They go hand in hand. So one is there is a caregiver turnover. So we have caregivers, especially for older adults. They go in and start a new job, and then they leave within less than a year. And that's paired down with an increased need for caregivers, because we have a problem of graying of America. So people are getting older more so than before, or like faster than before, in larger volumes, and we need more caregivers. So there is a gap in the communication training for those caregivers. That's not only for caregivers of older adults. It applies actually in the wider domain. But specifically, there's no specific training for communicating with patients to build that rapport, especially in the healthcare domain part of it, and to continue that training from one session to another. So let's say I visit a patient, or a patient visits me today, and then like I want to continue that conversation next week or later on in the week. So how to continue that? So how can technology help in this? So there's related work with other people as like creating a virtual agent for dementia patients and their caregivers, or creating a virtual patient with Alzheimer, and to explore modeling emotional and expressive pathologies there. On the technical side, there is prior literature of creating an older, like virtual human for older users to improve quality of life, or using embodied virtual humans as opposed to just like a voice-only virtual human, and that shows that increases social presence and engagement. So there's a gap in having those older virtual assistants or virtual patients that have a memory of what happened before of a conversation as part of the training. So our focus was on trying to create and design and develop a prototype that can capture that to train the caregivers of older adults, specifically in the communication and rapport building side of it, while creating a geriatric virtual patient that simulates that conversational and spatial awareness as part of a simulation. So, and we want to assess the usability, acceptability, and user experience with those caregivers. So the next section is about the system design and development. So the system workflow is you have a user, which is in this case a caregiver, and they have a HoloLens 2 on, where inside of that they see a virtual patient, a geriatric virtual patient in the room. And that patient is being controlled by a human controller, so that's the client. And when the user speaks directly to the patient, the human controller hears the response and responds back with pre-recorded responses in this stage. Later on, we're looking at automating that piece, but in this stage, it's pre-recorded responses, and they're saved into a database. So the way we got these responses, we had some interviews prior to this, to building the system, and we learned about the challenges, what a typical conversation would be, so that built into those responses. We also created a custom 3D model for a geriatric patient. So we looked at first to see, are there any ones that are pre-made that we could use, but we had a hard time finding something that is suitable in terms of like being old and wearing appropriately and being animatable for AR and VR applications, so to be used in real time. So we had to redesign this. We also got feedback from experts while doing the design of these characters, and we used Maya to create the character, and we 3D modeled character, accessories, clothes, etc. So, like for example, just like wearing a dress may be not a good thing, as in like wearing maybe like pants and multiple layers, they see that more in nursing home. So like, okay, we had to make these changes on the fly. So we rigged that to be animatable and created blend shapes so we could simulate the speech. So we created blend shapes for visemes and for facial expressions. So this is a snapshot of the visemes. Also with facial expressions, we modeled the basic emotions in there. And we created our own plugin in Unity and Salsa to integrate all of those together as part of the simulation. As for the patient responses and graphical user interface, so we had a collection of over 100 types of responses, and we categorized them into different sections, like some for introduction, some would always be there, like quick responses like yes, no, or not sure, can't hear you, things like that. And other subtypes related to like maybe sharing a story or passing a time by playing a game or having talking about like food or colors or things that are like you'd expect in a basic conversation to be in there. And those responses were stored in the database. We had audio pre-recorded for these. And the main goal was like, as part of the simulation, we want to make sure that we're simulating that awareness piece of it, whether awareness of specific objects in the room, so we use IoT devices, or whether awareness for a conversation, like referring to something that happened in a previous conversation. So awareness of people and the conversations. So the procedure, we had a within-subject design, and we had 16 professional caregivers, 15 female, 1 male, and they had 2 interactions, and before each interaction, we gave them some instructions. So for example, before the first interaction, we asked them to go in, introduce yourself to the patient, her name is Rose, and just like pass some time with her, so get to know her. So they did the first interaction, went out, and then went back again, as if it is like a second day, another day in the week or in the month. And we asked the caregivers to have a specific task, tell her that her son's going to be late today. And after that second interaction, during the second interaction, the patient shows that they're aware, so they address the person by their name. And this one, we knew the caregivers' names ahead of time in this section, but that could be automated in the future, maybe more in real time. And the patient also commented on things personal, like if the caregiver said, hey, I'm a UCF student, so they would comment on something like, okay, yeah, are you graduating next semester? Or something related to a piece of information that the caregiver gave in the first interaction. And after that, we asked the questionnaires for system usability scale and technology acceptance and open-ended questions. So this is what the study setup looked like, and you could see there is a human control station to control the responses. The virtual human is actually an augmented reality, so this picture, it's overlaid just so you could see what the participants would be seeing, and the participant just like has the conversation there. So the results of the study were, first of all, we measured the interaction time between in the first interaction and second interaction. And first one, the average was about 7.5 minutes, and the second one is a little bit shy of 5 minutes. And we checked how many average responses we had in there. So in the first interaction, there were on an average 71 responses. So and the second one on average 49. So it's roughly like 10 responses per minute that were triggered. These are short responses, they're not like long paragraphs, but just to get an idea of when designing for future simulations. And we measured the system usability scale, and we got a score of 78 out of 100. For reference, 68 is considered good, so anything above 68 is considered good. And for the technology acceptance model, we got a score of 28.5. It's out of 32. 32 is the max. And here are some selective, some select qualitative feedback of things that were that caregivers classified as positive. So one user said, "I liked how personal it felt. I enjoyed how it felt like I was speaking to a real person." Another person said the responses were quick and diverse and allowed for a real conversation. Another participant said visually appealing responses were appropriate, appreciated human interaction. And one person said, I think the software is great and would be amazing for nurses, for nursing students to practice. We also seek some suggestions, like what would be a good thing to incorporate in future versions of this. And one person suggested having family members to also interact in the environment, as opposed to just the older adult, and maybe implementing more organic responses from the patient. So in conclusion, we were able to design a prototype, check that it's feasible to train caregivers in communication rapport building, and it features a virtual patient that simulates awareness of the conversation and of objects in the room using IoT devices. And it showed that the system has a high usability and high technology acceptance. And here are the references, and do you have any questions?
Thank you so much. Any questions from the audience? Then I start with a question. You already mentioned there were some suggestions from the nurses on how to improve the system. I was wondering, are there any plans to assess the effectiveness of the system in the actual training, and how would you do that?
Let me repeat the question. Do I have any plans to assess the system?
Yeah, how effective it is.
As part of it, I don't have, yes, as in like effective in terms of like self-efficacy of the nurses.
Exactly,
or
yes.
social presence. So yes, we have data, we're still analyzing those. We have primary results for that, which wasn't ready for this presentation. But one of the things is like measuring social presence and measuring self-efficacy. Yes, measuring empathy. So these are measures that
yeah. Yeah, really cool.
Yeah.
And my other question is actually, of course, you have now this control panel approach, which looks super cool. Have you thought of somehow integrating LLMs into that?
Yes. Yeah. So we started looking into this. I don't have any data to share yet, but that is the next thing. As in, like, okay, now that we see that there is this is a usable system, this is something we could use. It has some preliminary data for like being effective. How can we automate this so it's more scalable?
Great. Thank you so much. Okay, a great round. Great, and thank you so much.
All right.
The next speaker is Baiqiao Zhang, and he is talking about becoming an animal, exploring the Proteus effect based on human avatar hand gesture consistency. Baiqiao Zhang is an undergraduate student in the School of Mechanical, Electrical, and Information Engineering at Shandong University, and his research interests include human-computer interaction and virtual reality.
Okay. Thank you for your introduction. I'm Baiqiao Zhang from Shandong University. It's my pleasure to be here and share our recent work. The topic of our paper is Becoming an Animal, exploring the Proteus effect based on human avatar hand gesture consistency. Everyone knows this guy. In the virtual world, avatars serve as the digital representation of the VR user, allowing them to engage in actions and immerse themselves in the virtual spaces. For the same person, using different avatars may lead to their different performance in human perception, attitude, and behavior, which is known as the Proteus effect. Our previous study have demonstrated the Proteus effect. The occurrence of the Proteus effect implies a deep sense of immersion in virtual reality environment. Many previous studies on the Proteus effect focus on the human avatars. Then how about using the animal avatars? In a recent study, Li et al. Developed a virtual environment where the participant embodied a cat avatar and play, revealing that the participant can connect themselves to the virtual role, such as a cat. They introduced the physiological concept of self-illusion to explain this effect. And how to assess the occurrence of Proteus effect? The occurrence of Proteus effect or self-illusion is important for VR experience, but there is a lack for an objective assessment method. When we use the first perspective non-human avatars, the characteristic of virtual hands may also induce relevant cognitive and behavior patterns in real human hands. Therefore, this study aims to explore an objectively method to evaluate Proteus effect in using non-human avatars through evaluating non-human avatar gesture consistency. This is our research framework. Specifically, to explore the Proteus effect under the non-human avatars from gesture features, we first construct virtual avatars and environment. And after that, we developed a deep learning model to recognize the human avatar gesture consistency. Finally, we conducted a user experiment to validate our assessment method, further explore the effect of avatar characteristic on self-illusion. This is the construction of virtual avatars and scenes. In our experiment, we created a pair of human avatar, a male or female, and created 3 non-human animal avatars that were chosen based on the hand similarity to human hands. Then we created an experimental VR environment. To achieve an objective assessment method, we developed a human avatar gesture consistency recognition model by these 3 steps. The first step is performing hand gesture when experiencing different avatars. The second step is building a dataset reflecting human avatar hand gestures. The final step is trying a recognition model to detect the human avatar gesture consistency. The 4 mentioned virtual avatars were experienced using the Pico 4 all-in-one VR headset. The Pico 4 captured the generated hand data through its front-facing camera. By combining OpenXR hand recognition information with Pico's hand recognition SDK, we finally extract 22 nodes from each hand. We built a hand gesture dataset to comprehensively cover the gesture's data information, representing each avatar as full as possible. Finally, we trained a recognition model to detect the human avatar gesture consistency. We conducted a 69-participant user experiment to examine the Proteus effect on the different characteristics of avatars, and we verified the effectiveness of our proposed method for assessing Proteus effect or self-illusion by detecting the human avatar hand gesture consistency. This is the different implementation of virtual avatars in our task: 1 human avatar and 3 animal avatars. This is the procedure of our user study. There are many 4 steps. The first step is that the participants to practice themselves. The second is they can selecting an avatar. The step 3 is they serve as an avatar to practice. The final is to perform the task. This is a participant familiarizing himself with the controls and the virtual world. According to our user study, there was significant many effect of avatar type on feelings of self-illusion. Human avatar led to significantly higher level of self-illusion. When we analyze the results on the human gesture consistency with the avatar, we found that using human avatar led to significantly higher percentage of human gesture during performing the task. And using non-human avatar led to significantly higher percentage of corresponding non-human gesture during the task. Finally, we could introduce an objective and real-time method for evaluating the Proteus effect in using non-human avatars based on detecting human avatar gesture consistency. Our findings reveal that the participants exhibit a significantly higher percentage of gestures consistency with their presently used avatars. And we discovered that the types of virtual avatars significantly impact the user's self-illusion. Utilizing non-human avatars can indeed evoke self-illusion of participants, although its level were significantly lower than this experience when using human avatars. We conclude that self-illusion may be a perceptual accident of Proteus effect even in non-human avatars. The characteristic of virtual avatars influence human self-illusion at a cognitive level, subsequently by affecting human gestures and at the behavior level. Thank you for listening.
Thank you so much. Fantastic presentation, thanks. Any questions from the audience? Yes, I'll just drop by.
Thank you. Hi, thank you for your presentation. I'm John, a PhD student from France. I really like the idea of using behavior for measuring the Proteus effect. How do you think, because this was solely like, we saw the shadow on the video, like it was only the arms that were modeled. I mean, at one point we saw like it was the arms of the cat that were floating. Do you think like a fuller avatar of the cat, like with the feet and everything, would have a stronger effect? Would it be kind of scary for people? Also, like the measure of the non-human gestures, it was mostly the arms, right?
Yeah.
Do you think they would kind of like start to walk like the animal, kind of?
Thank you for your
Very
question.
fun experiment.
Very interesting. And I want to answer the first question. Currently, we are focused on the hand gesture in the Proteus effect. We think if in our future work, if we can employ the full body of the non-human avatar, will induce the more deep Proteus effect. And the second question is about the hand gesture or other movement. We think other movement is our future work. We can conduct more experiment on such as walking and grabbing something, or even in the talking. Yeah. Thank you for the question.
Any more questions? Yes.
Hi, Marie-Louisa Fiedler from the University of Würzburg. Maybe I missed it at the beginning, but can you give us a short description and definition of self-illusion, what you've meant with that? Is it that I feel more like a cat when I have the cat hands?
Can you repeat your question? I can't.
Can you give us a definition of self-illusion?
Definition of self-illusion?
Yes, yes.
Oh.
Maybe I missed it at the beginning.
I think the self-illusion is defined in the related work of Li et al. In the TVCG 2022. And we think it's the accident condition of the Proteus effect.
Thank you.
Any more questions? That seems not to be the case. Then thanks again for our speaker.
Thank you.
And we continue with our last talk of this session. It's an online presentation, Art to Human, real-time 3D human appearance rendering from a single image. The presenter is Wang, and he's a master's student in the College of Intelligence and Computing at Tianjin University. His research interests include 3D vision and digital virtual humans.
Hello everyone, my name is Wang. I'm a master's student at Tianjin University in China. I'm excited to share our research, which is the first approach for real-time inference and rendering of photorealistic 3D human appearance from a single image. Realistic 3D human appearance rendering is becoming increasingly popular and important in immersive experiences. However, preview works typically require the multi-view camera inputs, making the system expensive to build and difficult to maintain. In addition, these systems are often complex to build, and only implicit rendering can be done. Our primary goals can be summarized into three main points. First, we develop a real-time 3D human appearance rendering system. Secondly, by using a single RGB camera and building an end-to-end reconstruction and rendering network, we have simplified the multi-camera setup. Finally, our goal is to create a high-quality 3D human appearance at a lower cost. The input to the system is an image from a single RGB camera. We obtain human geometry from the image and render it according to the camera parameters to obtain a high-quality no-view human appearance. The realistic work in our study mainly includes two categories. Most methods of real-time 3D human appearance rendering are flow-based neural rendering, and they are often limited to multiple camera settings. Another category of methods aims to recover a 3D consistent appearance for the human from an implicated texture field, but the rendered images are of low quality and the process is time-consuming. The work in the first row are flow-based methods. The work in the latter row is implicit texture field-based methods. Although the latest research has achieved realistic performance, none of them can combine single camera settings with real-time performance. Here is a pipeline of our method. Our method is based on an end-to-end nature network that performs high-fidelity color reconstruction of visible areas and previews reliable color inference for occluded areas. The core of our method is to propose a new representation named ZMAP. As shown in the video, we transform the visible point of the target view to the input view, thereby obtaining its depth in the input view. Therefore, the ZMAP can uniquely determine the position of the point in the texture field together with the image features. ZMAP as a bridge to connect the advantage of implicate texture field and explicit neural rendering. In order to ensure the multi-view consistency of the model, we propose a special fusion strategy when running the video. which fuses the render results of the previous frame with the current frame. During training, we propose a consistency loss. Specifically, we use the texture field of the input image to render two images with different views, called the reference image and the multi-view image. We map the visible points in the reference image to the multi-view image view and supervise the color of their corresponding points to ensure multi-view consistency. Finally, we built a low-cost real-time capture and rendering system that renders the 3D human appearance from a video stream captured by a common USB webcam. As a demo, our system can reconstruct and render the realistic 3D human appearance from a single 2D image in real time. In the follow sections, we compare our performance with other single-view reconstruction methods that cannot handle in real time. We compare our method with the baseline method on the T-Human2 dataset and the 2K2K dataset. Type-Fu demonstrates the ability to estimate reasonably accurate colors, but its performance is hindered by limitations in geometric estimation. On the other hand, while shells can produce results with accurate posture, it faces challenges in producing desirable results for humans who wear loose clothing, mainly because it relies heavily on simple priors. Our method can obtain high-fidelity rendering results with reasonable geometry and color. In addition, we also used in-the-wild images for testing to demonstrate the robustness of the model. Finally, we also try a lot of meaningful applications. We use panoramic images to render the 3D human appearance into a virtual environment, thus providing a more realistic and stunning virtual experience. In addition, we also try to render the results into a real sense of an AR application. In summary, our research proposes a real-time method for rendering 3D human appearance, contributing to a more immersive experience. We hope our contributions will be used to make more impressive experiences. Thank you for your attention.
Thank you very much. Are there any questions for the author? He is online on Zoom. It's Wang Yang. I have one question, and that is, I'm not sure, I think I should talk in this direction. Is the system available for use? So is the source code somewhere that the community can actually integrate this into our systems? Can you hear us? Test, test. Hello? That does not seem to work. Hello? Hello? Can you hear us?
Sorry, I should unmute. I will open my code for the community, yes.
It's going to be open source.
Yeah.
Ah, that's fantastic.
Because the code is very
Oh, that's very cool. And another question that I have is, what are the next steps for your system? So right now, it already produces really good results. Are there any improvements that you have planned for the future?
No, my question only use random learning, and in the future I will using the video information.
Okay, great. Any more questions from the audience? That seems not to be the case. Then thank you so much. Thanks, Yuan Wang, and thank you all for being here. This concludes the Avatar 2 session, so we are 7 minutes early. I assume nobody's going to complain a bit about the longer break. I have one more thing to say. If you go outside to the right on the staircase, there is a little QR code. We're doing an online survey where we want to know about the experience of the community with reproduction and replication studies. So if you have 3 minutes of time, that would really help us out. And that's really it. Thank you so much. Enjoy your break and the rest of the conference.